And this is your first homework problem, and this is it's a 6.9 from your textbook. It says the circuit shown in the figure is a model of a solenoid. Yada 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 yada. You can read about this. You have a resistance R, and you have an inductance L, and you have a supply voltage Vs, which is an input. And the resulting current activates the magnet, yada yada yada. Obtain the model of the current I given the supply voltage Vs. So they want a differential equation in terms of I sub t. Okay? So I could have asked for the same problem. I could ask for them obtain the system model for the voltage drop across the resistor, or even the voltage drop across the inductor. So let's try this one. So we're going to use the MASH method. So there's a MASH method and there's a node method. I didn't tell you anything about node method yet. So this is MASH method, where your unknown will be I, and you go around the loop. So here, what do we know about the voltage across the resistor? That's equal to I times R. I'm just listing what I know. So the V is equal to L di dt for the inductor. Okay, so this is voltage drop across the inductor. This is voltage drop across the resistor. Okay, so this will be, if I put a terminal, let me move this out of the way. Oops, yeah, then let me move this one out of the way. Never mind. I'm just going to start from the beginning. So from here to here, okay, this is your voltage drop across the resistor. That's equal to I times R, plus minus. And from here to here, okay, here to here, plus minus. This is the voltage drop across the inductor. That's your L di over dt. Okay, so keep that in mind. So let's start. When you go around the loop, I'm going to start from this point right there. Okay, the negative terminal of the voltage source. So I'm going to start with a Vs of t, that's your gain, equals, now it's going to be the drop. It's going to be the voltage drop across the resistor plus the voltage drop across the inductor. They're all function of time. Okay, all function of time. So that's equal to your I, okay, I sub t times R, plus you have L di over dt. Okay? So this is it. You have a system model for, in terms of I, system model of I. So I can rewrite it as di over L di dt. Move everything to the left hand side except for the source, equals the Vs of t. So this is your system model, and this is a differential equation form of the system model. So now this is part A. Okay, part A. So now part B says, suppose that you have a unit step and the initial condition is 0. Obtain the expression for the response. You have several options to solve this problem. One of them will be the trial solution method. So let's try the trial solution method. So you have L di over dt plus Ri, all function of time, equals your V constant. Okay, so this is valid for t greater than or equal to 0. Okay, so you can get away with not writing the unit step if you limit your domain, okay, for time, for positive time. So your homogeneous solution, I homogeneous solution, will have the form of C1 times e to the RT, okay, where it's going to be plugged into L di over dt plus Ri equals to 0. Okay? This is the homogeneous equation. So you'll find that this is equal to unknown constant. This is called the constant of integration. And then e to the R will turn out to be, so you have L times R plus R equals to 0. You'll have the characteristic which will be negative R over L. So you have negative R over LT. So this is just a homogeneous solution. For the particular solution, Okay? For the particular solution, you'll assume a constant A. Okay? A constant. Why? Because your V is constant. Okay? Your input is constant. So this is constant. Okay? Plug it into the original equation. You have L times 0, because this is constant. The derivative of constant is 0, plus R times A is equal to V. So you'll find A, okay, must be equal to V over R. So now I have a total solution. I sub t equals C, unknown constant, minus e to the minus R over L t plus V, capital V, that's your voltage source, divided by R. So this is your total solution. Then, so your step number 1 was here. Step number 2 is right there. And step number 3, okay, you combine them together. And step number 4 is apply your initial condition. I sub 0 is, what did I say? 0. 0. So you'll see I sub 0 equals C times e to the 0, which is 1, plus V over R. That's 0. That's 0. That's what that was given. So you'll find that C1 is equal to negative V over R. So what does that mean? Oof, I made it just in time. I just had enough space for this. So you have I sub t. Okay, I sub t is negative V over R, e to the minus R over LT plus V. I'm going to move this out of the way. Oh, I tried to move that out of the way. Yeah, I'll rewrite it. So you have a C equals negative V over R. Okay? So you have plus V over R. That's your final solution. Okay? So note, it has a time constant. This function, your homogeneous solution, has a time constant of tau equals L over R. That's how long it takes for the initial value to decay to e to the negative 1. What is e to the negative 1? Is it 37 exp negative 1? That's 37%. Okay, that's how long it takes for the response to decay. Only the homogeneous solution to decay to 37%. We'll lose 63% of the initial value. So this function, if you draw this, if you sketch this, it will look like this. We have I sub t, and this is t. This is going to be upside down decay function. We have a V over R. It's going to be the final value. It's going to start from 0, and it's going to approach. So what does that mean? What happens at tau? When time is equal to tau, which is L over R second. What will happen is you lose 63% of your initial value. Okay, so this number used to be 1. Okay, this number right there, okay, used to be 1 at time is equal to 0, and it becomes 37% at tau. Okay, what that means is this value right there will be 0.63% of a V over R. Okay. So you can find graphically, if I give you exponential function, it doesn't matter. It could be a decaying function, or it could be upside down decaying function like this. You should be able to figure out what the tau is just by looking at the graph. Let me pause. Let's continue with the second. So now let's try the second homework problem. It says to obtain the model of the voltage V out, where V out is the voltage across the capacitor and the resistor number 2. Yeah, instead of the current. Okay, we were expecting current, but no, they want the model of the voltage out, V out, given them the supply voltage Vs. So Vs is the input of the system. So if I use the mesh method, I'm going to start with the Vs equals. So I'm going from here, I'm moving around, okay, starting from the negative terminal to the Vs. So I gain Vs equals, now the voltage drop is R1 times I, the only current in the system, I, and plus the voltage drop across the capacitor and the resistor. Okay? So our goal right now is to get rid of the current. Okay? Get rid of current. That needs to be replaced. Needs to be replaced with VO, function of VO. Okay, something that has with the VO. Okay, so what do we know about this VO? Your V out, okay, a function of t equals 1 over c integral of I dt. Okay, I dt plus R2 times the current of the total current that's going around the loop. So I don't like to use the integral sign, so I'm going to differentiate once. So I'm going to have a V0 dV over dt equals 1 over c times I plus R2 times di over dt. Yeah? So if you recall, I'm trying to get rid of I sub t. Okay? How do we do this? So what I'm going to do is I'm going to solve for the I sub t from this equation and actually plug it into these two. Okay, those two. Yeah. So from the first equation, I'm going to call it 1. This is number 2. I'm going to solve for the I, which is your Vs minus V sub t minus V0 sub t. So this is all function of t divided by R1. It's going to go into those two places. So now I have dV out over dt equals 1 over c times R1 V source minus V out plus, now I'm writing the remaining term, R2 times the derivative of I, which is dV s dt minus dV out over dt. Okay, so what did I do? I just copied down equation number 2. Okay, equation number 2 with the I replaced with the V source minus V out divided by R1. So now I'm going to collect terms. So I have almost everything I need. So I see that I have a V out right here. Yeah, right here. V out right here. V out right there. Okay, I'm going to collect those terms. I'm going to put them on the left hand side. So writing from the highest order term, which is dV over dt first. So I have R2 over R1 on the left hand side. It's positive, plus 1 times dV out over dt. Okay, I just took care of these two terms. Now plus 1 over CR1 V out equals the remaining terms, the source terms will have they have to stay on the right hand side. Those are the non-homogeneous terms. You have R2 over R1 dV source dt, also a function of time, minus 1 over c times R1. That minus is plus Vs of t. Okay, so this is your final answer. This is a system model for V out, VO, which is much more difficult to obtain than the system model for the current. And amazingly enough, when you look at the left hand side carefully, it will be exactly the same. They'll have exactly the same coefficient as the ones that I would have gotten if I found the equation of motion, the system model in terms of I. So we try. So I'm going to do it in blue. So we have a Vs equals R1 times I sub t, or function of t, plus 1 over c times I integral I dt, plus R2, why did I write that? I. Okay? So if you differentiate once and then move the terms on the switch the left hand side and the right hand side, you'll have R1 plus R2 times d I sub t over dt. Okay? And plus 1 over c times I sub t equals the derivative of Vs over dt. Okay? So let's compare the left hand side. What's the characteristic root? That's equal to 1 over c times R1 plus R2. That's your characteristic root, minus. Okay? So let's look at the left hand side of this. If you multiply everything by r, you have R1 plus R2 times the dv out dt plus 1 over c. V out of t equals R2 times dvs over dt plus 1 over c vs of t. Okay. The only thing that's different about these two equations, well, there are plenty actually. Okay, so the first one, this one, is a model for the current. Okay, and then this one, the solution to the current equation, this is a model for the voltage source, the voltage out. But what do they have the same? The left hand side exactly the same, with the exception of this is in terms of I, this is in terms of a V0. Okay, so what does it tell you when you look at the characteristic root? Okay, for the homogeneous solution, you get the exact same thing. You have 1 over negative 1 over c times R1 plus R2. Okay, and then your homogeneous solution will look like, whether it's a V out or I, it will look like some constant. Let's call it C1, and e to the minus 1 over c times combination of R1 and R2 times t. Okay, so this is the homogeneous solution only. Yeah, and then they have the exact same time constant, and then that's true for a system, true for the system model that's a part of the same system. Whether you write down the equation of the system model for the V out or the current or the V out or the voltage drop across the resistor 1, it doesn't matter. They're all going to have the same left hand side. Okay, so that's the end of that's the end of the second homework problem. So let's move on to the third one. Let's try another problem. All these problems are, by the way, they're very difficult. Okay? And then soon I'll teach you a much easier method using impedance. So just hang in there. So let's see, I'm going to use the loop law, okay, around. I'm going to say this is my loop 1, and let's see, I'm going to say this is my loop 2, okay, loop 2, yeah, and then I have a node right there. So let's start with a node, actually. Let's start with that node. So the current junction law says the current that going into this node is the same as the current that's coming out of that node. That means it's I1 is equal to I2 plus I3. Okay, so that's equation 1. And equation 2 is the loop law for the loop 1. So that will be V1. That's the voltage gain going from the negative terminal to positive terminal. And then loss is L di1 dt plus R times I3. Okay, we have to make sure to use the correct current. This is equation number 2. And equation number 3 is your V2 equals, okay, you need a negative sign because your loop direction is in the opposite direction of the current for the loop 2 over the capacitor. So you have integral of I2 dt plus R times I3. Okay, that's your third equation. So let me read the question. It says obtain the model of the currents I1, I2, and I3 given the input voltage V1 and V2. So what it's saying is, I thought I was over. I thought this was over. I did write 3 equations and 3 unknowns. Isn't this it? Actually, when I looked at this is the correct solution too. Okay, because it is possible to solve coupled differential equation. Okay, but when I looked at the solutions, it actually wanted the system model for the current I1 only. Okay, so in terms of I1 only, so this is asking for 3 things. Yeah, so fine. So from here, simplify it so that to get rid of I2 and I3, and then that will be the answer to the first part. So this has 3 parts to the problem. So part A is to find the model for the current I1, get rid of I2 and I3. So let's see. I want to try my simultaneous equation solving skills. So what I'm going to do is I'm going to subtract 2 minus 3. Okay, 2 minus 3. Why? So I can get rid of I3. So I have a V1 minus V2, all functions of t, equals L di1 dt minus plus 1 over c times integral of I2 dt. Okay, this is still no good because I still have I2 to get rid of. So now what I'm going to do is I'm going to, let me see. I want to get rid of I3 from equation 1 and 2. So why don't I multiply equation 1 times R and subtract equation 2. Okay? Then I'll have R times I1. Oh, you know what? Let me not do elimination. Let me just do substitution. So I'm going to write equation 2. Okay, equation 2 with the I3 substituted. So you have a V1 equals L di over dt, di1 over dt, plus R times, instead of I3, I'm going to use I1 minus I2. Okay, so I have new equation 4 and 5, and 4 and 5 are in terms of I1 and I2 only. So my goal is to get rid of I2. So what I'm going to do is from equation 5, I'm going to solve for I2. I2 is I1. Let me see, I'm going to move the I2 to the other side and divide by R. So I have I1 plus L over R di1 over dt. Okay, so far so good. Then minus V1. Did I do this right? I moved I2. Okay, I need to isolate I2. Okay, I moved the I2 over to the other side, and I moved the V1 to the other side. Oh, I see my mistake. I have to divide by R. I forgot to divide by R. So now I have an expression for I2. I want to plug this into here. Okay, equation number 4. Okay, before I do that, I'm going to actually differentiate the whole thing. So I'm going to differentiate equation 4 with respect to time. I'm going to change the left and right hand side. And I have L d squared I1 over dt squared plus 1 over c times I2. Okay, I differentiated it, so integral disappeared, equals V1 minus V2. And let's not forget to differentiate it. So now my goal was to get rid of I2. So I'm going to plug it in, and I have L di1 over dt squared, don't forget square, plus 1 over c. Then I have I1 plus L over R di1 over dt. What am I doing? I'm just substituting it in. I'm just replacing I2 with this expression. Okay. Equals V1 dot minus V2 dot. Those are the derivatives with respect to time. So if I clean this up, I have L di1 square over dt square. Now the next term to write is that one. Okay, the purple one. So that's equal to plus L over RC times di1 over dt. Okay, and I have plus 1 over c times I1. And then these terms, I'm going to highlight them. These terms Oh, actually, there's only one term. This term right there does not belong on the left-hand side. So you have to move to the right-hand side. So you have dv1 over dt. I'm writing them. That is the d over dt minus dv2 over dt. They are functions of time. And plus 1 over cr times v1 of t. Okay? So this is your system model. Okay? This was actually quite difficult to plan. I actually had to pause the video and do this in my head. Do this, I had to practice before I can present it to you. So there is another method using impedance, which is much easier. Okay, so we're gonna get to it soon. In fact, the next lecture.